All right, so it says a point on a curve 2y equals x squared. We're looking for what point is nearest to 4, 1. So if you were going to draw this out just to get an idea of what it looks like, it's going to be y equals x squared over 2. So I'm just going to graph that out really quick. So it looks something like this. Maybe, doesn't really matter. Okay, and then 4, 1, let's just say it's, I don't know, right here. Doesn't really matter. We're looking for what is the closest distance between this orange point and then some point on the red. Okay, it's probably not going to be one of these points up here. It's probably not going to be one of these points over here because there's one that's like, you know, right here somewhere. Okay, we don't know the exact value though, so we're going to have to figure out using optimization how to do this problem. All right, but that picture just kind of helps get an idea in your head of what you're looking for. All right, so let's break this down. We're looking for the nearest, so that is the distance. So first thing we're going to do here is write the distance formula down, and we're trying to find the minimum distance between this. So distance right here, it's going to be change in x. Well, one of the x's is 4, so I'm just going to put a 4 in there right away, plus the change in y squared, which is just going to be y minus 1, quantity squared, and then we're doing the square root of all this. Now we need to figure out the derivative of this so that way we can figure out where the mins and maxes are. Okay, and this is not the easiest derivative in the world. It's probably actually the hardest one that you're going to be really doing for an optimization problem. So it's a good one to really make sure you're paying attention to. So d prime, I'm going to do the derivative of this. It's going to be 1/2. So I'm bringing the 1/2 down from the outer layer times that inner layer. And instead of y, I'm actually going to just write x squared over 2. That way everything's in terms of x. And since we subtract 1 from the power up here, it's going to be negative 1/2 there. Okay, now we did the derivative of the outer layer, but we still have to multiply by the derivative of the inner layer there. Okay. Also, we got rid of this y here and wrote x squared over 2. Okay. So we're going to multiply by that inner derivative now. So it's going to be 2 times x minus 4. So we're doing the derivative of this thing right here. Times 1. So we don't have to do much else on that one. And then we're going to multiply, or we're going to add the derivative of this thing right here. So let me do a different color. So it's going to be plus 2 times x squared over 2 minus 1. And then we still have to multiply by that inner layer's derivative, which is going to be 2x over 2, which is just times x. Okay. Let's make sure we're doing this right here. Okay, that looks right so far. Does anybody notice anything I missed? I just don't feel like doing this whole problem and then going back and going, oh man, I totally forgot something. We're good. I think that's good. Okay. Trust your gut. All right, now if you distribute this 1/2 here, these all become 1. So it makes it a little bit easier to look at. From here, I'm going to simplify all this, which seems a little crazy here, but so you're going to have x to the third over 2 minus x plus x minus 4. So this part right here that I just wrote down is just all of this right here simplified. We got some simplifications here with that. Okay, and then we're going to divide this all by this green right here. It's a square root on the bottom, so I'm putting it on the bottom here. Now the great thing about this is you can actually ignore the denominator because we're setting this equal to 0. You could set it equal to or undefined, but it has to be defined on the actual graph. So we're going to kind of ignore the or undefined on this. And the only thing that we have to worry about for the 0 is the numerator. So we don't actually have to worry about the denominator at all. If you want, you can multiply both sides by it, and then it's gone because you're multiplying it by 0. That is perfectly legal. And you're going to be left with x cubed over 2 minus 4 is equal to 0. So this is all just algebra at this point. In fact, after that green step, like this whole d prime thing, the rest of it's all algebra, so it shouldn't be too bad. Let's multiply both sides by 2 here. So we get 8. And the answer for this one should be 2. X equals 2. Okay. Now, if this was a, strictly a multiple choice problem, there is only one critical number. So the only answer where x is equal to 2 would be B. But let's just keep going on this. Let's actually test the interval, because in free response, you would have to do that. So we have x equals 2 here. Let's make a critical number line. Okay, we're going to put 2 on it. And then D prime tells us what D is doing. All right, so put something like, I don't know, 0 in there. This should be negative. Put something that's infinity, maybe. It'd be positive. Okay, so that means we're decreasing to increasing. If you were sketching the graph here, it would look something like this. Down, there we go. And then up. I wrote relative min, not absolute min, because I actually don't know if it's increasing and decreasing, because there was other critical numbers we didn't even bother trying to check. So it doesn't really matter. The main thing is that this is a relative min here for a x value that's actually defined where it's at. We do need to figure out the y value as well on this. So you would have to plug it into the y equation, which we have right here. Okay, so if you plugged in 2 there, you get 4. 2y equals 4. So that means y is also equal to 2. So 2 comma 2 is the final answer for this one, which is B.